In this video, we will be comparing sparse matrix distributions obtained by different partitioning methods. The first method is based on the fine-grained model, which translates a sparse matrix into a hypergraph, where all the non-zeros become vertices of the hypergraph, and every row gives rise to a row net, a hyperedge, containing all the non-zeros, all the vertices of that row, but also every column gives rise to a column net. It's a big hypergraph, of course, because you have as many vertices as there are non-zeros. Then, if we look at the processes within a row of the matrix, we call the number of such processes lambda I, and that means that in the best case you will have lambda minus I communications within a row. And similar for columns, we have mu j, which is the number of processors that are present in column j. So when we partition this hypergraph using some partitioner, then that models exactly the communication volume of the parallel sparse matrix vector multiplication. Partitioning for the fine-grained model is expensive because there are so many vertices. What would we like to have? First of all, we would like to have all non-zeros in a row together. And then we also would like to have all the non-zeros in a column together on the same processor. And finally, we would like to have our cake and eat it. So, what is the solution to this? We can't have it all, really. So the solution is to split the matrix A into two parts. AR, which contains rows, and AC, which contains columns. AR we call the row matrix, AC the column matrix, and they are disjoint. And all the non-zeros in AR, in a row of AR, by design, they stay together. And all those in the columns of AC, they also stay together. So if this split is favorable, we get close to what we really want, and that is non-zeros in rows being together and non-zeros in columns being together. And then when we have formed these two matrices, AR and AC, we put them into a matrix B, which is larger. In case the matrices are square, which we will assume here, then if the matrix A is n by n, the matrix B is 2n by 2n. And so we put AC in the left bottom and AR in the top right part of the matrix. But AR we transpose so that the non-zeros in the rows that stay together become non-zeros in the columns of the B matrix that stay together. So for the B matrix, we want columns to be together. And then on the diagonal, we put identity matrices, and that's really to connect the rows and columns. We'll see that in more detail later. So here's the simple split of the matrix. We base the split on the number of non-zeros in a row and in a column. The number in a row we call Ri, the number in a column we call Cj, and then for a non-zero Aij, we have to decide if it goes to the row matrix, shown in gray, or to the column matrix, shown in black. It's also marked by a C. So the simplest criterion is really take the row count, the column count, and if the Aij is in a row that has fewer non-zeros than the column J, then it's more likely that the non-zeros in the row can stay together. So we choose for the row, and otherwise we choose for the column. There's one exception. In case a row contains only one element, only one non-zero, then of course it has a lot fewer than in the column, but that row cannot be broken, it cannot be cut. So we still assign it to the column, so it can participate there and help in reducing communication there as well. So once we have done this, we create our matrix B. You see that all the black non-zeros, they end up in the left bottom part, and the gray non-zeros, they end up in the right upper part, but then transposed. So you will recognize them. And then we also have diagonal entries, and that's really, if you look at, for example, the column 1, which has 2 gray entries and 1 black entry, then that column is being split. It becomes column 1 of the matrix B. And then in the top, you see a square which has both colors, which connects it to the row. And so this is what we have for the diagonal entries. Now, if the row would have been empty, like row 0, then there's no need for the diagonal entries. So we remove them. And then once we have this B matrix, what we can do is we want to keep the columns together. So we assign complete columns to processors. In this case, column 0 is blue, column 1 is red, etc. And we take care that there's a good load balance, but we do not count these new diagonal non-zeros. We only count the non-zeros of the original matrix. And here we see we have a communication volume of 4, because you see that 4 rows of the B matrix have both a red and a blue non-zero. So that's why the communication volume is 4. Now we can translate A back, we can translate B back into A by reversing the process. So everything that's in the left bottom block of B just ends up as it is in A. But in the top right corner of the matrix, we see 3 red non-zeros. They are also transferred into A, but then they are transposed. And for example, row 1 of the matrix B will end up as column 1 of the matrix A. So this is how we translate this back. And there's a nice property which says that basically communication volume is preserved. And here we say that the number of processors in column J of A, that's our final output, equals the number of processors in row J of B. So expressed in the formula, if we take mu J of A0, A1, we get that it is lambda J of B0, B1. So now a deep thinking question for you. Why is this the case? And maybe to help you, have a look at column 4 of the B matrix. Note that we start counting at 0, so 0, 1, 2, 3, 4. So it's the last column before the separation line. So why is this formula true? Okay, so this was a hard one. Look at column 4 of the matrix B. This column only has a single owner, which is blue, and it is already visible in the diagonal element B44, which is blue, but which is also part of row 4 of B. So if we want to know how many processors there are in column 4 of A, our final outcome, we just need to look at row 4 of the matrix B. That's why. Okay, so we have a similar thing for columns and for rows of the matrix A, and this helps us prove that the communication volume that we measure in the matrix A is the same as the volume for the matrix B when we split it like this. And so that means, that's the good news, that we can get a two-dimensional partitioning of A by just doing a one-dimensional partitioning of a slightly larger matrix B. And one-dimensional partitionings, they are faster. And this way, but two-dimensional partitionings, like of A, they have more possibilities to get close to the optimum. Okay, so let's see how this works out in practice. We have a test set of sparse matrices taken from the SuiteSparse collection, which was formerly called the University of Florida collection. We have a matrix from integer programming, MIP1. We have India 2004, which is a web link matrix. Asia, a road network. Cage 14, we've seen the cage matrices already from DNA electrophoresis studies. And we also have a random geometric graph. So it's 5 very different matrices, but they all have between 10 million and 30 million non-zeros. The number of non-zeros per row or column varies a lot, from 155 for the MIP matrix to only 2, which is the road network. Road networks, they don't have many connections, so it's a very sparse matrix. Okay, so in this rather full table, we see both the communication volume, that's the quality of the partitioning, and the time in seconds, that's how fast you get the partitioning. And in all cases, you get the result within a few minutes. And then we have examined 3 different methods. The original Mondriaan method, which is called local best, LB, then the fine grain method, and the medium grain method, which we discussed in this video. And well, you win some, you lose some. It looks like in general, the medium grain method has a lower communication volume than the other methods. So with a few exceptions, like the Asia matrix, but in general, you could say that the volume of medium grain is less. And if we use a geometric average, geometric mean, we can summarize all these results. And then we see that the medium grain has 70% of the communication volume of the local best, and fine grain has 83%. So medium grain is really better in this summarizing metric. And as concerns the time it takes, medium grain is almost as fast, a little bit faster than the local best, so that's good. And and fine grain is really slower. It has to solve a hypergraph partitioning problem for a bigger hypergraph. So that's what we can learn from this. And this is then based on a limited number of experiments, partitioning into 2 or partitioning into 64 for 64 processors. But that's what we have here. And why did I choose the geometric mean to present results and not the arithmetic mean, the common average that we know? The reason is that in this case, every problem instance, so matrix and number of processors, has the same influence. And the geometric mean is defined by multiplying all the numbers, for example, k numbers, and then taking the kth root. So for 2 numbers, a and b, the geometric mean is just the square root of a times b. A nice property of the geometric mean is that if we want to normalize, for example, one method compared to the Mondriaan method, then we could normalize first all the results and then take the geometric mean, or take the geometric mean and then normalize. It doesn't matter. And then it also doesn't matter if you have 3 methods, how you normalize it compared to which of the 3 methods. So that's a very useful property. There's another way of presenting results, like for 10 matrices, but also for more, and that is a performance profile. Here I show a performance profile of the communication volume for the three methods, and higher is better. So how should you read this picture? Well, when you look at the line for 1.5 times the best cost is 1 to the left, just the best of all three methods that we found. And then if you look at 1.5 times the best cost, and you go up, you see that local best solves 70% of the problems within that factor of 1.5 of the best. So it's close to the best in 70% of the cases. But the medium grain method, for example, it's higher up. It solves 100% within 1.5 times the lowest volume. So this is a picture that gives insight. And even if a method fails for a certain matrix and a number of processors, then you can still use the other results in here, and you can't do that with the geometric mean. So this is a way of showing results for many matrices. For example, you could take all the 2,833 matrices of the SuiteSparse collection and also have the number of processors vary from 2, 4, etc. up to 1,024. No problem. You can summarize all of these results in one performance profile. Okay, so to summarize, the fine-grained method is in principle the most general and should be able to find the best solution. But in practice, because of the favorable properties of keeping rows and columns together, the medium-grained method achieves better results, lower communication volume. And to summarize results for tests, we introduced two very useful methods. One is using the geometric mean, and the other is performance profiles. And now I have a final question to you. Here is a matrix A. You haven't seen it before. Form from this matrix B, from A, a matrix B by the simple method. And if there are ties, you should break them by giving preference to the column matrix AC. And then, once you've formed B, assume that you're prescribed that it has to be distributed by the cyclic column distribution. Translate the result then back to a distribution of the matrix A. And then please verify that indeed the communication volume for A is the same as the volume for B.